Alright, let's get started. Okay. Thank you all for coming to NREC 20th anniversary event. Okay. So we have a series of speakers today. The first one is Dr. Raj Reddy. He is the Moussa bin Nasser University Professor of Computer Science and Robotics. Raj Reddy also played a very critical role in the founding of NREC. He is the founder of Robotics Institute. He was the Dean of School of Computer Science during the creation of NREC. Okay. So he certainly played a very critical role. Dr. Raj Reddy, again, was the Dean of School of Computer Science from 1991 to 1999. His interests include AI, human-computer interaction. He has many professional honors, probably too many to mention all of them, but some of them is Fellow of IEEE, Fellow of Acoustical Society of America. He also has several awards from different countries, including Legion of Honor from France, Padma Bhushan from India, and ACM Turing Award. He also has won many other prizes, including the Okawa Prize in 2004, the Honda Prize in 2005, and the Vannevar Bush Award in 2006. So I would like to welcome Dr. Raj Reddy.
I think I'm already wired, yeah. Good morning, good afternoon. It's such a great pleasure to be here. I didn't think I'd still be around at this time. I'm probably one of the ancient people around. Takeo and Marshall, the three of the 5 directors are here of Original Robotics Institute, which is wonderful. So what I thought I would do is spend the first half kind of reminiscing on the formation of Robotics Institute and NREC, and then show you some videos, and then talk about what are the possible futures for robotics in the future. And unfortunately, the number of things that we could be doing in the future ultimately is governed by the money we have. There are lots of things we can do. What we will do depends on what research funding we are able to get. So I'll just leave it as kind of a wish list at this point. So the Robotics Institute was formed in '79. And before that, in the 70s, we were already doing robotics, but in a smaller scale. At that time, Dick Cyert, was the president. And I remember he called Newell and Angel Jordan and the Dean of Engineering at that time, and me, saying, why aren't we doing robotics? Because he heard the phrase somewhere and they wanted to know why we were not. We said we are already doing it, but to do it on a big scale, we'll need $5 million or something. Okay, he said, this is in $1980, right? $1979. So he went and talked to people at Westinghouse. Westinghouse at that time was one of the major companies in Pittsburgh, and they had multiple divisions. And one of the divisions was headed by it'll come to me in a minute. Basically, all I did was make a presentation like this, and they approved $5 million. No proposal, no nothing else, because it was all wired in already, I think. So it was great that was the first and only proposal where we got multi-million dollars without writing a proposal. So, and their interest at that time was, they were one of the major manufacturing companies, and their interest was automation of manufacturing. And the other broad interest I had was autonomous vehicles. Basically, I came from Stanford. Even in the 60s, we were already working on autonomous vehicles. And Hans Moravec, who came and joined us at the beginning of the institute, was one of the people that built the Stanford cart. And those were the two broad themes: manufacturing, automation, and autonomous vehicles at that time. And you have to remember, the computers in those days were a million times slower than today, so everything was a pain. Just getting even an image captured was almost impossible. And but nevertheless, we made a lot of progress. And people like Red and Takeo who led the way at that time. Takeo was already a young full professor in the 1980, and was probably the dominant force in vision by then already. I used to dabble in vision in the 70s. As soon as Takeo joined us, I said, I don't need to work on vision anymore, and stopped working on it. So in the autonomous vehicles, we had a number of expectations, not only land vehicles, but also sea and air. And Takeo and his students did the autonomous helicopter at that time. But to my disappointment, we are not next to an ocean. CMU is not. So we never got started on autonomous sea vehicles. My own expectation even today is ultimately harvesting of the oceans is going to be one of the major uses of robotics, basically. Now and then, we have not gotten there yet, but we will. And it was great that Red Whittaker joined. He used to be a young assistant professor in the civil engineering department. Once we got started, he left civil engineering and joined us and became a full-time researcher, and has been a great source of inspiration for many of the people, including the formation of this NREC at that time. So I'll just show you some quick videos, and then we'll kind of go to
a specific application of our work on flexible manufacturing cells. A specific application of our work on flexible manufacturing cells is an installation at the Westinghouse Turbine Component Plant in Winston-Salem, North Carolina. This has been a collaborative project between university research personnel and Westinghouse engineers. The system consists of two computer-controlled robots, a large, heavy-duty open die forging machine, and vision-based parts identification and measurement systems. The role of the research team at the university has been to design and initiate the computer operating system for the cell, to design and install the robot controllers and grippers, and also to develop the two vision systems. The first robot withdraws a heated billet from the rotating furnace. In the manufacturing process, stainless steel billets are hot forged and formed into preforms that, at a later stage, will be closed die forged into finished airfoils. The gripper used here is made from Inconel. A key research area in the development of the cell has been the coordination of machine actions. This has been done with a rule-based system that operates on dynamic databases describing each of the machines in the cell. Another important research area has been the development of the vision gauging station for component measurement and feedback to the machine tool in order to compensate for hammer wear. The finished preform is placed in front of a light panel, which produces a very crisp silhouette. The preform is analyzed by a solid-state camera, and an Automatics vision system is used to collect data. A horizontal line scan of an object cross-section is taken, and from the many views of this slice, the component cross-section can be reconstructed. It is critical that the width, thickness, and cross-section of the preform are accurately...
Okay.
The Terracator is a pilotless outdoor vehicle for research into autonomous navigation. It is viewed as a shuttle whose initial missions will deploy artificial vision for guidance and acoustic sensing for obstacle avoidance. Future missions will support mapping, path planning, and will deploy a fuller contingent of perceptive sensing. The knowledge gained through Terragator research will be important to autonomous vehicle applications as occur in construction, mining, material handling, and the military. The Terragator is more capable, adaptable, and survivable than its interior counterparts. The Terragator's power and scale overcome obstacles and grades that pose entrapment, tip-over, or pitfall to lesser locomotives. The Terragator can be configured as a low-speed, high-torque climbing machine, or by gearing changeouts as a higher-speed machine for gentle terrain. Two competing measures of a land navigator are its ability to negotiate terrain and its ability to step its way along intended paths. The Terragator is challenged to do both, and over three-dimensional terrains having general surface characteristics. Although the Terragator's six-wheel drive provides superior locomotion, the indeterminacy of its skid steering requires gyroscope and tilt meter corrections to ensure heading. Our research agenda will further develop the software pilot and will add hardware such as ranging devices and actuators to orient sensors.
So this was, I think, around 1985 or so, 86. At that time, the computer was still very slow and the computer vision was very slow. So as you can see, the highest speed you could go at is a few miles an hour.
We recently built the NavLab.
This one.
Recently built the NavLab, a test bed for research in robot navigation, image understanding, and the role of human interaction with intelligent systems. The NavLab is a roadworthy truck modified so that researchers or computers can control the vehicle as occasion demands. As a mobile navigation habitat, it accommodates researchers and significant computing on board. Because it is self-contained, the NavLab is not subject to telemetry bottlenecks, communication faults, or dependence on stationary infrastructure, and can travel to confront navigation problems at a test site. Driver controls...
We'll show you some of the videos. We didn't coordinate who is going to show what. But the great thing is, you fast forward 30 years, right? From 1985 to 2015, suddenly the autonomous cars are in all of our future. They're kind of predicting by 2025, more than half of the cars sold in the country will be autonomous. And there are some other, they're predicting all the cars that will be sold will be by law autonomous, because they will be safer and consume less power, and can be more easily controlled. So NREC was formed, I think it started, what, 1994?
Yeah.
Tim, when did the funding come?
The state was 94.
94. Who was the governor at that time?
Governor Casey.
Okay. So Governor Casey gave us $3 million. I had nothing to do with it. It was mostly Red Whitaker, and I just knew about it. Takeo might have known more. He was the director at that time. And but by 95, we had this whole building. I think the city gave the land, and the state gave the money for refurbishing it. And I think I can truly say it has been a great investment for the state. When you look at all the things that came out of here, and that not only the jobs created and the research done, but also the number of startups that have come out of here, I think it's just great. It has been a great investment by the state. So right from the beginning, the main difference between, say, Robotics Institute and REC was, one was mainly looking at advances in technology to create next generation robots of all kinds. Whereas here, the issue was, let us start with the applications in mind and see what needs to be done to make the applications work. And right from the beginning, that seemed like a great separation. So the applied robotics part of the NREC kind of started with these kinds of things, basically agricultural robotics, mining robotics, nuclear, and defense. And again, you'll see some examples of this. I'll stop there. I'm sure many of you have done created all those things, so I don't need to show you those things. So I thought we'll spend the next 10-15 minutes talking about where we go from here, what kinds of things. You can think of it as both missing science that may be done in Robotics Institute and missing applications, the applications of the future that will always be there with us. And many of the things I'm talking about are ideas that we started with even in the 80s. It is just that we haven't had time and money to go do them. But I thought I'll give you some sampling of those things. One of the early problems we faced was the problem of how to colonize the planets and so manufacturing in the moon. Obviously, you could not airlift the whole factory there. So the issue was, is there a way we could create a self-reproducing factory? And so I gave this problem to Fritz Prinz, saying, can you create a self-reproducing lathe? And he tried for a year and came back and said it can't be easily done because of the size of the cylinder he had to create was the size of the lathe, and there was no way to create it. And I said, okay, we can make it in two parts, and made them together, and that's what we ended up doing. And so the idea of creating every manufacturing system, all the CNC machines and lathes and milling machines and so on, in a self-reproducing environment was a very challenging problem at that time. It still is. And I don't know of any obviously self-reproducing factories other than the human being. And we need to kind of keep thinking about it. The basic idea is simple, namely, can you create an electronic DNA which you would drop on the surface of the moon and it would make itself into a factory? And we assumed that maybe not everything can be done on the planet. Maybe some things can be airlifted. So that's why we said 90% self-reproducing factory. That some things can be provided from here. And so that kind of concept, I think, is still important. There are a lot of fundamental problems that have to be studied and we should work on. And that would be done, say, in Robotics Institute. Maybe it will be done here too. The next one is autonomic systems as opposed to autonomous systems. The difference between autonomic is your heart beats autonomically. You don't tell it, beat heart every time. It just keeps beating for 100 years or so without you having to tell it, right? So the idea is you need to have systems in the environment where you're not controlling them. You kind of grow them and let them loose, and they are doing certain jobs that need to be done, maybe collecting the garbage, And or maybe there are all kinds of things you can imagine where a system that's completely self-motivated, self-aware, that would do things by itself without you having to kind of guide it in any way, shape, or form, would be one of those things. In general, in cyber physical systems, these are what we call always on, always working, and always learning systems. You can think of an app, for example, that's kind of monitoring what you do and predicts what kind of news you're going to do, what you're going to read. It's all in the cloud, it's always on, and it looks at your bank account, and it looks at your grocery shopping lists and everything. And even before you wake up, everything is done for you. So you just, coffee appears at your bedside, and it's all done. So those kinds of systems, always on, always working. The biggest problem there turns out to be for conventional apps, you need to have a cell phone that's always on. It'll run out of battery today, right? So I don't know how many of you have used Amazon Echo? Raise your hands. If not, you should invest in one, because I'm very fond of it, because I worked on speech for 50 years. This is the first time. I used to say 10 years ago, there's no way in my lifetime you'll be able to have a speech-to-speech conversation with a machine, open population, unrehearsed speech, right? And we are not there in Vision. I think that'll happen in Vision 2 in 10, 15 years. Right now, this is the first system I've seen. The reason I find it very interesting is Siri and Cortana and others also do that, except they're not personal. With Amazon Echo, you can actually say, order, some groceries for me, or play music, or read me the news. So whatever you want, it's all fully, and there's no keyboard, nothing. It just, you just speak to it, and it's always on. And the reason I used to give talks about it 25 years ago, saying my personal assistant would be like my secretary. I would kind of tell it what to do, and it'll figure out how to do it, right? And so there are a number of problems. The clever solution Amazon did is they solved the power problem by saying this is not mobile, it's going to be plugged in. And so you plug it in, and it's always on. And if you want to ask it, saying, Alexa, play music, you kind of give it by the name. Otherwise, it's simply there listening. You can be talking to anybody, and it works, right? So those kinds of systems, I think, are going to be the next generation autonomic systems. The next one are what I call sustainable systems. Right now, most systems, including human beings, need care and feeding, and they need to be fed and for them to survive. You need systems that can survive all kinds of difficult situations. The worst possible scenario you can think of is a nuclear holocaust. Can you build robotic systems that will survive that kind of a system and then go save the people that have been affected by it, and then kind of help to create the new civilization kind of thing. In general, sustainable systems have many interesting attributes, just like sustainable economy, the sustainable economies or sustainable cities and so on. And you can sit down and define what a sustainable robot is. And that would in fact have an interesting set of research issues. And Nine Sigma systems that never fail, never fail. 1 in a million or a billion hours of something is, and secure systems, because the question in all of these things. So these are 5 different kind of basic types of robots we could be building in the future. And as I said, again, it depends on who believes these are important and funds it. And I think defense systems might be one that might be interested in all of them, defense sciences. But The same is true in manufacturing. You know, we stopped working on manufacturing seriously after the 1990 because manufacturers were doing lots of things. I think only David Bourne was doing some metal sheet bending and other kinds of things in the 90s, but other than that, we didn't do too much. But there are a number of concepts there that are still important and relevant. We should probably keep in the back of our mind when the right opportunity occurs. You say, yeah, we know how to do that if with some appropriate funding. The first one is what is called a virtual factory. What that says is, when you need to manufacture something, you don't build a real factory because they're very expensive things, and especially for semiconductors and so on, it runs into billions of dollars. So ideally, you want to simulate the factory, kind of build a complete simulated factory, simulate all the various attributes of the factory, and see if it will produce the throughput and within the time constraints, and basically are looking at cost, time, and quality. And if the simulation can tell you about those parameters, then I think you have so building virtual factories as a technology would be something that you want to do. The second one is reconfigurable, programmable factory. We used to talk about it even in the 80s. Takeo and I remember. The question was, can you build a factory in Pittsburgh which would produce Toyotas today and Hondas tomorrow and something else day after? And in general, by purely changing of software, it'll produce different kinds of things. This is already done in some sub areas, like semiconductor manufacturing. There's not that much. They produce different kind of chips in the fabs in China and in Taiwan, and they produce different chips every day. The third one is what is called a networked factory. A networked factory is one where there's a customer, they're the product producing factory, they're suppliers, right? They're all interconnected, and things are being produced on demand, and different kind of products on a continuous basis, right? And we used to call it parts on demand. In fact, I asked Paul Wright to see if he can design one of these things, and even after he left here, he continued working on it. He's now a chaired professor at Berkeley. And Paul, it took a long time to produce. So it's called mechanical Moses. There used to be a thing called Moses where we used to produce semiconductor chips on demand, right? In the 80s. Mechanical Moses was a way of producing mechanical parts where you design and you ship it off and comes a part to your exact specification. In those days, it was not obvious. We had stereolithography technology, but now with 3D printing, you don't need to send it out. You can print it right there in your office. This kind of parts on demand. But a network factory is an expansion of it, not just for a part, but a whole product line or set of products. And the whole issue is, can you integrate the whole supply chain, and the customers, where you're producing exactly one of a kind at the same economies. It's called economies of scope than economies of scale, right? You can produce one of a kind at the same cost as mass-produced parts, right? And microfactory means what it sounds like. Can you build a tiny factory? Right now, we build a factory for cars that produce 100,000 to a million cars a year, right? Basically, and economies of scale dominates that whole thing. And for a long time, many of us would come and go and bug them, saying, you're producing Cadillacs, you're not producing 1 million Cadillacs or 1 million Rolls Royces, you're producing only 10,000 of them. They're only maybe 20% more expensive and in smaller scale. But if you created a micro factory in every city and produced these things, you reduce the inventory, you reduce transportation costs, you reduced various other things. Why can't we have a micro factory? And that's still kind of, again, you see examples in specific domains where this is like a microbrewery to produce brews, right? You can do that. But it's not kind of widely accepted principle. By the way, all these ideas were around in the 80s. They still are relevant. I was a member of a study committee for the National Academy in maybe in the 90s, because we used to talk about it in the 80s, but the report came out sometime in the 90s from the National Academy that talks about these kinds of manufacturing ideas for the future. So this is kind of general directions in robotics. What about applied robotics? I think a lot of the exciting futures in robotics will come in the applied uses of the robotics that we put into. And I come from a little village in India. I go there every so often. In the old days when I was growing up, people were happy to have a job, and they would go work in the field and planting rice or whatever it is that needed to be done. These days they don't want to work. They say it's too hot. If you're sitting in your office and not working, why should I work? And so it turns out, even though a lot of things need to be done, there are not enough. And even though there's 1 billion people, there are 1 billion too. Nobody wants to work on this, terrible jobs in agriculture or mining or defense or disaster and so on, because they are both dangerous and uncomfortable and not worth their. I think all of them have the same kind of a property, namely, these are jobs that human beings don't want to do. And so, if only we can create future systems and solutions. Again, these are not new, though. You have at NREC have already been doing the first 4 or so. What is happening? The main difference between then and now is the so-called IoT, Internet of Things. As a result of Internet of Things, you can have a sensor and a processor on every part or every device you build. And again, in case you think these are all new ideas, I remember Takeo built an imaging sensor with processing built on it. When was it, Takeo? 80s? 85? Something like that. So these ideas have been around. It's just that they get, when you have 1 million times more computational power, there are things you can do today that could not be done 30, 40 years ago. And what you find is, in many, the whole big push on smart cities and so on, is there are disruptions of services. There are essential things everybody needs. They need water, they need food, they need electricity, and so on. And whether we want it or not, one of them gets disrupted. And right now what happens is, when a power grid breaks, goes away, it may take a day or 2 to fix it. The other day, Delta Airlines, their computer system went down, and the entire global flights had to be canceled or changed. And they claimed they lost $100 million in lost revenues in a day or 2. And these kinds of things should not happen. If it did happen, we ought to be able to figure out before they happen. It's called preventive maintenance or preventive medicine in the case of human beings. Before something in some part of your body fails, you discover that and either repair it or replace it. And so those kinds of things, I think, are in the future, namely understanding sense, think, and act in a small device, where your sensing is built in, processing is built in, and even microsurgery is built in into the same chip, into a small system that can wander through your body or wander through systems, and do whatever it is that needs to be done. And so the difference between what was possible 30 years ago and what is possible now is, with million times more computation, million times more memory, and million times more wireless bandwidth. I don't know if you remember the bandwidth we used to have long ago. The Wi-Fi systems only came 20 years ago. The initial Wi-Fi systems we were lucky if we had 1 megabit. Now the standard is 50 or whatever megabits. We're talking about a gigabit and 10 gigabit wireless in the terahertz broadcast frequency range. And those kinds of things will be there in 10 years, 15 years. So the question is, we should prepare for that kind of future and then do what we can. I already mentioned IT-enabled manufacturing. The personal assistants, this has been always a big science fiction kind of a thing. We all would like all kinds of, we would like a gopher whom we can tell, go do this, go do that, clean up this, and get me a cup of coffee, whatever. And it's both, again, it's the cost, time, and quality. How well can they make a cup of coffee and bring it to you without spilling it all over the house becomes an important issue. The same is true with respect to chefs and chauffeurs. Chauffeurs, I think, are gone away because we will have autonomous cars. I'm sorry, I'm running over time, so let me stop here. With that, I'm happy to be part of this 20th anniversary symposium, and I wish you 20 more years or 50 more years of successful NREC, and Marshall and Herman will lead the way. Thank you.
So we have time for a few questions.
So the only claim to fame I have about NREC is Dave Panos and some other people had kind of helped to build up this place. And then there was some problem which I never fully got into. So the provost said, we need some good technical leadership. So it turned out Red had 2 PhD students, John Barris and Tony Stentz, and I knew about them. So I said, would you please be the head of this thing? This was in 95, 96, I think. And that was the best decision I made, and it worked out well. Thank you. Okay. Yeah.
So Dr. Herman gave an interview a couple of days ago about whether or not self-driving cars are going to become a reality, and he said that it's really difficult and maybe it's unlikely. What's your position?
Oh,
I want to speak for you.
they are a reality. They will be much more, and partly because there's a huge incentive for doing it. I can tell you more about it, but I want to digress for a minute. Red and I went to General Motors in 93 or 94, and I said, we already have the technology. We want to work with you. Why don't we, build a car as soon as, it'll still take 10 years or 15 years. They said, number one, they said, don't tell us, we're already working on it. This was, So we said, okay, it doesn't matter, we'll tell you if you steal our secrets, that's okay, but. And the sad part is, if they had started then, I think by now we would, in the US, would be kind of in the leadership position. Right now it's kind of Germany and Japan that are in the leadership position. So with respect to where we would be, I'm a betting man, right? I think I'll still be around in 2025. If 50% of all the cars sold in 2025 are not autonomous or autonomously able, like the Tesla, that they'll drive, but you can drive too, I would be very surprised. Okay. Now, most of the things that are remaining are not technical, because there was an accident, in Elon Musk's Tesla car, but compared to the 40,000 people or 50,000 people that die in fatal accidents and the number of accidents every day, everywhere, one accident doesn't crash the whole industry. And the benefits far outweigh. And the most important one is the fact that you don't need as many cars. You can have 1/10 as many cars. You don't need garages. You can get rid of all the garages, because basically people are building more and more garages, and people are building more and more parking spaces, and parking meters, and all of that will go away, because the new technology. One of the things you need to do is to say, supposing I don't have conventional cars, what will happen to the world? How will it be different? I'm not a kind of urban planner, but if I were, I would be saying, let's not build any more garages. We don't need them, okay? And these kinds of things. But slowly, the great thing about Uber kind of joining forces with NREC and CMU is the fact they have a great incentive to kind of get out of the driver provided Uber services. So that you call, and a car comes up and it knows where to take you, and you can maybe even speak to it, saying, take me home, and it'll figure out where to take you, and so on. And that type of solution will change the whole economics of automotive industry. For example, you don't need to make as many cars. Right now in the US, I think we sell 15 million cars a year or something like that. And we don't need to make 15 million anymore, maybe only 5 million. That will transform the automotive industry. A lot of people will lose jobs as a result. And the same is true with respect to jobs that we all have to do, including taxi drivers and so on. So just sitting back and saying, what are the implications of a fully autonomous, global society, car. And a lot of things, all the people that are providing current supply, systems, the whole supply chain. If you draw a circle around Detroit, about 100-mile circle, in Ohio, Indiana, everywhere, there are all kinds of manufacturers who provide parts to automotive industry. And all of them have to rethink their future too. And my own feeling is we will go fully electric within 10-15 years. All the cars will be electric, and they won't make noise, they won't cause pollution. And I think, so there are all kinds of futures we can kind of think about. That will be quite a societal transformation. And if I were in that industry, I would start planning for my new job. Where would I get it and what kind of job? Because many of those jobs will disappear. They will disappear. Okay.
Anybody else?
Actually, just following on from that, what do you think is the biggest obstacle for making that work for software?
Yes. Basically, the technology is there. It's been there since Red demonstrated it long ago. And right now it's mostly societal, namely the government has passed the regulations. 15 states or something have already set some guidelines. There's still 35 states that have to adopt it. Second, liability And all of those, I think, will take care of themselves because there's a lot of incentive. So, for example, I don't know if you know, when Musk created Tesla, he also had to create a set of charging stations all around. And so I was with a friend of mine, he said, oh, I'm running short of power. I need to stop there and charge up so that I can get home or something. So there are all kinds of new things that you and I won't think about, but they're there. So I think I can't think of any. I tend to be an optimist, and you have to be an optimist to be in AI and robotics. So, and so it's like what Simon said. Simon said, "We'll have a computer beating chess champion in 10 years or something." It took 40 years. In the scale of things, in the scheme of evolution, 10 years and 40 years is nothing. So whether it happens in 10 years or 15 years, it will happen. And you just have to kind of plan for that future. Because lots of things are happening. But the interesting thing to me is the evolution of the smartphone, right? Until 2005-06, computers were only used for computation. Now you have a device which senses, thinks, and acts, a robot for all practical purposes. And that's what we used to talk about. A robot is sense, think, and act engine. And computers never used to have sensors. You couldn't see, you couldn't speak, you couldn't see, and have vision. Those of us who were in the field knew that this would happen. I remember writing a paper about 4-in-1 mobile device and trying to sell it to Sony. Maybe, I don't know if I talked to Takeo about it, and said, Sony, you should be building these things. This was in 1995 or 3 or something. But I'm glad, when it happened, I was blown away because not just because we always talked about GPS and speech and vision type sensors. I never thought about barometer, and this phone has 12 or 15 sensors. Maybe 3 or 4 of them we might have talked about. The rest of them are all built in. Once you have that kind of capability, the main thing I'm waiting for is, without violating my privacy, for this system to become a weather station. There's absolutely no reason why we can't know the weather in every part of this world with this type of a device. If all of them combined can come together to provide a collective intelligence of the weather, then you can predict weather much better than today. Everything that you need is already here. The location information, the temperature and pressure and various other things. There's no reason why I would not be willing to share it with anyone else, except I may not want everybody to know where I am on a given day, but that can be anonymized and shared globally. Once you have that, then if there's a tornado that's going to happen, we can all get a warning sign saying, hey, there's going to be a tornado in your neighborhood, find a safe place. What we call guardian angel apps. You can build these things, and that will have truly transformative effect on those things.
Thank you.
Okay?